Hi everyone! In this video we're going to go over a few reactions of monosaccharides. So the first reaction is acylation. So as we know, sugars or monosaccharides are very soluble in water. If you've ever had a sugary drink, you know that sugar can dissolve very easily in water. So it can be difficult to isolate and purify sugar. So let's just write that monosaccharides are soluble in water. So they're difficult to isolate. So one thing we could do is turn all of the sugar's hydroxy groups into acyl groups or esters, and then we can isolate the monosaccharide. So let's start with a sugar here. So again, notice that sugars have a lot of these OH groups, which is what makes them very soluble in water. And again, it can be hard to isolate. So what we're going to do is react this with something like an acid anhydride or an acid chloride. Either one works. What that's going to do is turn all of our hydroxy groups into esters. So what I'm going to do here actually is I'm going to abbreviate this acyl group as AC. And that way it'll be a little bit easier to draw. Ooh, I'm doing terrible with the chair conformations today. It's been a while since we've done those. Okay, so all of those hydrogens will be replaced with that acyl group. And now we have esters. So now that everything is an ester, the monosaccharide can dissolve into an organic solvent, and then it's going to be a little bit easier to isolate the monosaccharide. So let's just write here that the ester derivative of monosaccharides are soluble in most organic solvents. And are easily purified. And then we could do analysis on it and kind of see what the structural makeup is of the original monosaccharide from there. There's another reaction we can perform with monosaccharides, and that is alkylation. So instead of turning all of those OH groups into esters, we can turn them into ethers. Let's see, so let's draw our sugar again. Get some practice with our chair conformations since it's clearly been a while, even for me. Okay, what we can do is react this with excess methyl iodide and silver 1 oxide. So this is kind of similar to that reaction we saw with amines. But in this case, what we end up with are ether groups. So all of the hydrogens on the oxygens will be replaced with that methyl group. Okay. Now, another reaction that we can perform with monosaccharides, we can form what's called a glycoside. So earlier we talked about how sugars are typically found in their cyclic hemiacetal form. So we kind of went over all the different ways we can draw those cyclic structures of our sugars. So let's just draw one of those right now as an example. This is just the same one I've been drawing. And one thing that we can do is we can react this with methanol and hydrochloric acid. And this is going to give us something called a glycoside. And we're going to end up actually with two products. So we're going to end up with the alpha anomer and the beta anomer. Let's see, so we've got the alpha anomer, and the OH group on that anomeric carbon is going to now be an ether, but all of our other OH groups are actually going to stay the same. So only the anomeric OH group is affected here. And then we'll also draw the beta anomer down below. Okay, so our original molecule here is the, let's see, cyclic hemiacetal. And then our two products are the glycosides. Now, glycosides we can also refer to as acetyl groups or acetyl molecules there. Okay, so again, the top structure is our alpha anomer. And this would form in, let's see, so 66% of our products would be the alpha anomer. And then the beta anomer is down below. And 33% of our product would be the beta anomer. Okay, so the last reaction we're going to go over in this video is epimerization. So remember last time we said that epimers are diastereomers, and we'll actually write this down. So they're diastereomers that differ in a stereocenter or chiral center other than the anomeric carbon. So let's draw D-glucose in its open chain form. So OH is on the right, The next one's on the left, and then the next two are on the right. And at the bottom, we have CH2OH. So what we can do is react this with NaOH and water. So this is going to be base catalyzed tautomerization. And we're going to form an intermediate that looks like the following. And this is called an ene-diol. So notice that we formed a double bond between the top two carbons there. And we also turned our aldehyde into an alcohol. So that's our ene-diol at the top there. Okay, so now if we react this further with base and water, the intermediate will go through tautomerization again back to an aldehyde. However, in the process, we get a mixture of chiral centers. So I'll try to draw both of these. I didn't give myself enough room as usual. So I'll draw the first one at the top. So the first product, OH will be on the right again, similar to the starting material. And then in our other product, see if I can squeeze it in. The top chiral center will actually be flipped. So the OH group will be on the left instead of the right, like we would expect. So the second carbon ends up changing, and we get two different products here. So the top product is just D-glucose again. That's the same as our original structure. The bottom structure is called D-mannose. Let's see if I can fit that in here. So we formed an entirely different sugar in this process. Now, the reason I'm showing this to you is because clearly, as we've said in the past, we don't want to end up with a mixture of products. If at all possible, we want to try to get just one product. So chemists tend to avoid reactions with bases and carbohydrates because otherwise you get a messy mixture and it can be difficult to separate those sugars. Okay, so we're going to stop here for this video because in the next video we're going to discuss how to reduce monosaccharides and also how to oxidize monosaccharides. We'll also talk about how to increase the length of a sugar, so how to add more carbons onto a sugar. And then we'll also talk about how to decrease the length of the sugar. So how do we remove carbons from the sugar? So I will see you then.